In 1953, a Douglas aircraft hit Mach 2, twice the speed of sound, the fastest piloted flight ever recorded. Years earlier, another Douglas prototype reached 470 miles per hour on propellers alone. 6 experimental aircraft were built, each to solve a different problem. None entered production. Yet every one reshaped the future of flight. This is the story of Douglas's boldest machines and why the ones that never served mattered most. In the spring of 1947, the Douglas D-558-1 Skystreak rolled out onto the dry lake bed at Muroc, its bright scarlet fuselage reflecting the urgency of a new era. The Skystreak was not meant for combat or records. It was a flying laboratory designed to answer a single question: how do jets behave as they approach the sound barrier? With its straight wings, a single Allison J-35A3 turbojet, and a cockpit packed with precision instruments, the Skystreak offered engineers their first real look inside the transonic regime, a region where airflow over the wings suddenly changed and control could slip away in an instant. Test pilot Bill Bridgman became the public face of the program, logging more than 150 hours at the controls. His flight notes describe a machine that was both responsive and unpredictable. On one run, as the needle crept past Mach 0.85, Bridgman reported a sharp spike in control force, sudden, almost jarring. The ailerons, once crisp, grew heavy and sluggish. Pressure maps from the wing revealed shock waves forming along the leading edge, confirming what wind tunnel models had hinted. The straight-wing jet was hitting a wall of air resistance that no piston plane had ever faced. Engineers pored over the data, mapping the exact moment when stability faltered, and controls felt as if slicing through thick syrup. The Skystreak's flights exposed the dangers of shock-induced control reversal and the limits of the straight-wing approach, yet every data point became a stepping stone. The findings fed directly into the design of the next generation of jets, including the swept-wing F-86 Sabre and the D-558-2 Skyrocket. The Skystreak did not break the sound barrier, but it gave American engineers the tools to understand and eventually conquer the invisible boundary that had held back aviation for decades. The D-558-2 Skyrocket took the lessons of the Skystreak and launched them into a new realm, one where jet and rocket power worked side by side. Engineers at Douglas designed the Skyrocket with a single goal: to push past Mach 1 and then keep going. Its swept wings sliced through the air, but the real breakthrough came from its mixed-power propulsion system. A Westinghouse turbojet got the aircraft airborne and up to speed, and the reaction motor's LR-8 rocket delivered the raw force needed for supersonic flight. NACA's chief research pilot Scott Crossfield became the name forever linked to the Skyrocket's ultimate achievement. On November 20th, 1953, Crossfield strapped into the cockpit, ran through the transition checklist, and ignited the rocket at altitude. The acceleration was immediate and fierce. At 78 seconds, his airspeed indicator pegged at Mach 2. Crossfield later wrote that when the needle hit 2, he felt the aircraft surge forward, as if it were being pulled by an invisible rope. For the first time, an airplane had flown twice the speed of sound in level flight. The flight was more than a record. It was a data-gathering mission. Onboard instrumentation captured pressure distributions, shockwave locations, and control surface responses at high Mach. Engineers pored over these numbers, building a foundation for future supersonic designs. The Skyrocket's successful rocket and jet transition set the standard for high-speed flight checklists, procedures, that would become routine in the X-15 program and beyond. The mixed power concept, once seen as risky, proved its worth by delivering the most complete high Mach dataset of its era. The Skyrocket's legacy lived on in every aircraft that aimed for the edge of the envelope. Ed Heinemann and his team at Douglas set out with an audacious goal. They wanted to build an airplane that could unlock the secrets of supersonic flight. The X-3 Stiletto was their answer, a machine that looked more like a dart than an aircraft. Its fuselage stretched long and razor-thin, barely wide enough for a pilot and a row of instruments. The wings were swept back 35 degrees and measured just a few inches thick at the root. They were designed to slice through shock waves instead of fighting them. To keep weight down, the structure relied heavily on magnesium alloy, a material both lighter and trickier to work with than aluminum. Every inch of the airframe was shaped to minimize drag, from the sharply pointed nose to the tiny, almost knife-edged wings. Underneath, a pair of Pratt & Whitney J-48 turbojets promised more than 7,000 pounds of thrust. The hope was clear. If the X-3 could maintain its shape and strength at high speed, it would reveal how to build the next generation of supersonic fighters. But the design pushed every boundary, and the team knew they were working at the edge of what materials and engines could deliver. Flight telemetry from the X-3 Stiletto revealed a story of ambition colliding with the realities of high-speed aerodynamics. Despite its sleek profile and very thin wings, the Stiletto struggled to reach Mach 1.2, falling short of the Mach 2 goal. Test pilots reported a phenomenon that few had encountered before: inertia coupling. At high speeds, a sharp roll input could trigger violent, uncontrollable pitching and yawing, a dangerous dance that left even experienced pilots fighting for control. On one flight, the aircraft snapped into a rapid spin, forcing a hard recovery and grounding the program for weeks while engineers pored over the data. Ed Heinemann later described the X-3 as a brilliant failure, not because it achieved its design targets, but because it exposed the hidden dangers of slender high-speed jets. The post-test memos and flight logs became essential reading for the next wave of designers. The drag rise documented near Mach 1.2, much higher than predicted, sparked Richard Whitcomb's area rule theory, which would reshape every supersonic aircraft that followed. The X-3's legacy was not in speed records, but in the caution it brought to the drawing board and in the engineering breakthroughs that emerged from its setbacks. The XB-42 Mixmaster stood out in a world still dominated by piston engines, aiming to prove that speed did not have to come from brute force alone. Willis Hawkins and his Douglas team placed two Pratt & Whitney R2800 radials deep in the wings, driving a pair of contra-rotating pusher propellers at the tail. This configuration was more than just unconventional. It was a calculated attempt to slice through the air with less drag than any bomber before it. With the engines buried and the nose left clean, the XB-42's lines were as smooth as any jet to come. On test flights, the aircraft reached a top speed of 470 miles per hour, outpacing every other piston-powered bomber of its era. But the promise of raw speed came with a price. Vibration rippled through the long drive shafts, especially at high power settings, and engineers struggled to tame the resonance. Flight logs detail repeated adjustments, yet the underlying mechanical complexity never quite faded. The Mixmaster's numbers were impressive on paper, but every hour in the air revealed how much effort it took to keep that performance under control. The XB-42 proved that aerodynamic ingenuity could push piston technology to its edge, but also showed just how much complexity came with chasing the last few miles per hour before the jet age truly began. Retrofitting the XB-42 Mixmaster into the XB-43 Jetmaster seemed, at first, like a shortcut to jet-powered bombing. Engineers removed the complex pusher-prop system and installed a pair of General Electric J-35 turbojets, cutting new side intakes and reinforcing the rear fuselage to handle the new stresses and heat. On paper, this conversion promised a fast, economical path to a jet bomber, but the reality proved much less practical. Herman Johnson, the test pilot, recorded multiple engine flameouts, 4 incidents in just 30 hours of flying. Each event forced a full inspection, grounding the aircraft for days at a time. The J-35 turbojets, still early in their development, produced less thrust than promised and struggled with reliability. The cost of structural reinforcement, new ducting, and system upgrades quickly erased any savings from reusing the old airframe. By the end of testing, the price tag for each converted Jetmaster matched that of a purpose-built jet bomber. The XB-43's limited performance and chronic engine issues convinced Air Force planners that adapting piston designs for jets was a false economy. The program's abrupt end made clear that the future belonged to aircraft designed for jet power from the start. The XB-48 stepped onto the runway as Douglas's answer to the strategic Air Command's demand for a jet bomber that could bridge the gap between piston-powered giants and the next era of flight. Its straight wings stretched out from a low-slung fuselage, carrying 6 jet engines packed into streamlined pods beneath each side. On paper, the 8-engine configuration promised high speed and long range, but the test flights soon revealed the limits of the straight-wing approach. As the XB-48 accelerated toward Mach 0.85, engineers tracked a sharp rise in drag, far higher than predictions. The data showed a critical Mach number of 0.81, and every knot past that threshold came at the cost of efficiency. Worse, repeated high-speed runs uncovered a more serious problem: microscopic cracks forming at the wing roots. Inspections, after each sortie, found fatigue spreading through the spar joints, a warning sign that the structure was reaching its limits. Reports from the Air Materiel Command made it clear the straight wing was a dead end for bombers expected to cruise at transonic speeds. The Air Force, under pressure to field a truly strategic jet bomber, shifted its focus and funding to the swept-wing B-47. The XB-48's data, especially on wing root fatigue and drag rise, fed directly into the design standards for the B-52, shaping how future bombers would balance speed, strength, and survivability. Though the XB-48 never entered service, its lessons became the backbone of America's next generation of heavy jets. Today, every leap in aerospace, from quiet cockpits to composite wings to reusable rockets, carries echoes of these bold experiments. When the next breakthrough arrives, it won't be by accident. Progress demands risk, and the future of flight still depends on those willing to build what no one else dares. Thanks for watching.